Okay, our next section is localization. It's today's last session. So we have 3 papers in this localization session. So our first speaker is Mohammed Ibrahim. So he is a 5th-year PhD student from Rutgers University. And today, he will share their experience about time-based localization with a commodity Wi-Fi hardware. Thank you.
Good afternoon. So this is our work, a joint work with GM Research about an experimental study for fine-time measurements, Wi-Fi fine-time measurements. So Wi-Fi time-of-flight tracking have been attracted many researchers. Great techniques have been proposed during the last 2 decades, following multiple improvements, reaching recently decimeter level accuracy. Now we have the 82.11 2016 includes a fine-time measurement protocol for Wi-Fi ranging. And the Wi-Fi chipsets already released in the market that has the fine-time measurement support. So let's talk about the protocol a little bit. The protocol works as follows. The station starts to initiate the fine-time measurement process by sending a fine-time measurement request and wait for the ACK from the access point. And then the access point starts to, after the acknowledgement, starts to send a fine-time measurement frames, waiting for the ACK while logging the transmission and the reception time, repeating this multiple times, and then calculating at the end the round-trip time while excluding the delay or the processing time on the both sides. So the contribution of this work, that we first verify the accuracy claims for this fine-time measurement protocol, and we introduce and calibrate an open platform for conducting Wi-Fi time-of-flight measurements to the research community. And this is using the 8260 Wi-Fi card and its Open Linux driver. We also develop a systematic methodology for measuring the performance of time-based ranging systems to enhance the repeatability of such experiments. So let's start first a little bit of background. So with the speed of light, 1 foot per nanoseconds, the signal propagates omnidirectionally and in the environment reflecting from multiple paths. For this example, let's say we have the direct path takes 10 nanoseconds, and the 2 components reflected from the wall takes about 22 nanoseconds. And with this 12 nanoseconds different, we need an EDC with an enough sampling rate in order to distinguish between the first component coming through the direct line of sight and the second components coming from the multipath. So the challenges of that we faced in this work, we were working with a fine-time measurement black box. There is no details about the fine-time measurement ranging system, and most of the implementation details are not really documented, and most of the implementation, like how we calculate the transmission, the reception timestamps, synchronization, correcting for the processing time, all of that are implemented in the proprietary firmware. Finally, there was no also much information about how to extract measurements through the open drivers. So the question here, how we can extract these measurements and how we can evaluate the fine-time measurement black box. So first, we introduce our open Wi-Fi fine-time measurement tool. First, about the hardware details. So there are several vendors that support the fine time measurement standard. We picked the 8260 Intel cards because it has the Opel Linux driver while supporting the fine time measurement. However, we found that it still needs further modifications in order to be usable for a fine time measurements to experiment with these cards for a fine time measurement. And in the next slides, we refer to this Wi-Fi card as an Wi-Fi card A. Also, we found that these cards in the access point mode, it only supports the 2040 megahertz channels in the 2.4 gigahertz. On the other side, we found also that there is a commercial Wi-Fi access points that supports the fine time measurement requests out of the box. We actually confirmed that there was actually 2 in the market that supports that, and we picked one of them, and we refer to this access point as an access point B in the experiments. On the software details, we use the IWL driver from the Linux Core 30 along with the firmware version 31. So first, let us talk about the access point side. How we can configure the access point to work as a responder to the fine time measurement requests. So usually through in Linux, they use the host APD in order to configure an access point, to configure a node as an access point. However, this configuration doesn't automatically configure it as a responder. So what we did, we modified the IWL driver to activate the responding feature when it's configured as an access point, and made this patch available. So after configuring the access point, we need to initiate the fine time measurement process through the from the station side. So the station initiates the fine time measurement process and calculates the round trip time. 2 options. We have 2 options here for initiating the process. First one through the Linux debugfs, or we can use IW command tool along with a patch that enables the station to initiate the fine time measurement process. And initiating station needs to acquire specific information about the access point, of course, like the frequency, the MAC address, and the bandwidth. So here is a simple demo about our tool. We have the station, we have 3 access points. The station starts to, our script starts to scan the surrounding access points and acquire the required information, and then starts to send a fine time measurement request to these access points. Can either send to all the surrounding access points or only the ones that support the fine time measurement. And then after the successful measurements, after the successful process ends, then it reports the fine time measurement, the distance in centimeters, along with the round trip time in the picoseconds. So let's move to the second part, which is the experimental setups that we used. We have 2 setups in this evaluation. The first one that we use are 2 small form factor PCs, which is the orbit nodes that we have in the lab, containing the Wi-Fi card A, configuring one of them as an access point and the other one as a station. And here's the setup. We also have the setup 2, which uses the access point B, the commercial access point, while we're still using the form factor, the orbit node, as a station. And there are the details about we use the 6 dBi omnidirectional antenna. We use the 6 feet cables and PVC pipes in order to fix the antennas on a specific height without disturbing the signal. And for the ground truth, we used 400 feet measuring tape along with Bush laser distance measurer. So the second thing that we introduce is a systematic accuracy evaluation. Here we wanted to gradually introduce additional reflectors in the environment that add multipath propagation, starting with the ideal case, the outdoor open space, while we have a single bounce coming from the floor and the direct path. And then we add more and more reflectors, one at a time. So here we have 2 reflectors from the wall, adding another second component for the multipath. And then at the end, we reach the complex indoor environment with a lot of reflections coming from everywhere. So the idea here that we want to propose a repeatable experiments that can be applied for any ranging system. So let's start first with the ideal case. We have a station and the access point. And here's the ground truth is the dotted line. First is this is while we're using the setup one, we can see that the estimated distance has an underestimation, consistent underestimation of the distance, has an offset with a 5 meters, around 5 meters for the Wi-Fi card A. And then when we move to the access point B, we can see that this underestimation is gone, and we can achieve actually the meter level accuracy. So, but as we see that this offset is affixed, so we can easily subtract this offset. So once this calibrated, we can achieve the meter level accuracy in the open space environment. So there is a figure here. So there is a figure here, but I don't know what it's not showing. So we have here the same setup, but while we are already using the cables that corrects for the offset. And we can see that here, with using a Wi-Fi card A, while using these cards while using these cables that corrects for the fixed offset, we achieve again the meter level accuracy in an open outdoor space. Then we add another reflector. So there was a picture again here, I don't know where is it. So it's the same thing as the setup that I mentioned here. That we have the outdoor open space along with a wall from a building, and we try to change the distance between the transmitter and the receiver, and this reflecting the second reflector. As we can see that the distance actually over and underestimates the distance, the ranging system over and underestimates the distance as we move further away from the reflecting wall. Here we reach the most complex setup that we have, which is the indoor room scenario. We compare here again using Wi-Fi card A and the access point B. As we can see, is still the Wi-Fi card A is being affected heavily by the multipath, while it's using the 20-40 megahertz channels compared to the access point B that is using the 80 megahertz channel. Is that we can see that the multipath effect is minimized on this yellow graph. We have a lot more experiments that we did in the paper, but due to the time constraints, I'll just focus on the main results. So here we have the mobile environment, how this affects, again, gives us an over and underestimation to the distance, along with if there is an effect of the multipath, indoor and outdoor. So, but the main thing here that we can see that the multipath affects this ranging system even for the higher bandwidth. Then we need to have a correction technique that corrects this fine time measurement ranging error. So what we try here that we assume, okay, that if we know already given the displacement of our short distances, we know that it can be estimated accurately using the motion sensors. We can adapt the usage of the triangular inequality to correct for the ranging system. So if we have a ranging distance, we have a measurement D1, and then the station moves to another point 2, then we can have a limit on the second measurement based on the previous measurement and the displacement. So finally, we had this, to augment all the results, we have an indoor localization evaluation. We have 3 access points in a cubicle office, and we show that with the Wi-Fi card A, it achieves 5.2 meters, and then when we correct it, approaches 4.2 meters, and then when we move to the Wi-Fi access point B with the higher bandwidth, achieves 3.8, and after the collection, it achieves 3.5. So the conclusion that our results confirm that meter level ranging is possible in open space outdoor environment once we calibrate this ranging system. In indoor environments with multipath, both ranging and positioning errors increase to about 5 meters, even when the line of sight reception is not blocked. And unless the deployment is dense enough to operate at higher bandwidth, at 80 megahertz or so, the results can be improved. And unexpectedly, the ranging system for some configurations significantly underestimates distance, as we can see that there was this 5.8 underestimation of the distance. And finally, with the dense deployment of the access point that can reach higher, with an access point that with the high bandwidth signals, the accuracy is expected to improve. So more information about our tool are available on our website. And this is the end of my talk. Thank you.
Our next speaker is Professor Rami Roy Chandahari. He's a professor of both computer science and ECE at UIUC. So he has a lot of awards in the last few years, and I want to highlight his SIGMobile Rockstar winner 3 years ago. Yeah, so I think his talk will be dealing with those inertial sensors for 3D orientation measurement. So let's welcome the speaker.
Thank you, Jay. Is my microphone working well? Okay, great. The title for today's talk is Closing the Gaps in Inertial Motion Tracking. When we wrote the paper, we thought it was very interesting, but at 5:30 p.m. today, it'll be a boring and incremental talk. So if you don't understand anything that's going to go on, then it's my fault. If you understand something, it's totally your credit, because this is not going to be an applications talk. This is going to be a little bit of a boring incremental talk, okay? But let's get started. This talk is most of the work is done by my student Sheng Shen and Mahant Gaura, and I just take the credit. Let's get started. Inertial measurement units, IMUs, most of you have heard of them. They're actually composed of accelerometers, gyroscopes, and magnetometers. And these are the sensors that are almost there in many of these smart devices today, smartphones, smart watches, drones, goggles, sports balls, rackets, shoes, etc., right? And they've had wide applications in motion tracking, right? Because with these sensors, you're able to understand how these objects are moving, okay? So there's a lot of work in inertial motion tracking, and essentially the question we're asking is, if you have these data from the IMU, the accelerometer, the gyroscope, and the magnetometer, can you develop motion tracking algorithms, the output of which will be a 3D trajectory or the 3D motion trajectory of the object that you want to track, okay? This is an open problem in mobile computing. No one has been able to solve it yet. This paper doesn't solve it either, but we make some progress, okay? And I've been struggling to kind of explain our algorithm quickly, but I've failed mostly. So we'll really start from scratch, because only if I tell you things from the beginning will you have some notion of what the problem really is and where the intuitions are coming from. I may not finish talking about the whole paper, but I figured that even if you understand what the problem is, that is better than not understanding anything. Okay? Great. So before I begin, there's one prerequisite slide that I want to kind of present up front, which is about rotation. Okay? All of you know, or you might have forgotten, but I can help you refresh. Rotation is a function that essentially rotates a vector from one position to another position. So over here, there's a vector 1, 0, and 0, 1. If you rotate it by 90 degrees, it rotates and the vectors change. And rotation can be expressed as a matrix, all of you know that operates on different vectors. And here is an example of a 2D matrix. Of course, it can be 3D as well. So if you apply rotation on a 3D coordinate framework, it will actually change it to a different coordinate framework. Okay? That's all you need to know mathematically for what I'm going to talk about for the rest of the 15 minutes. Okay? Great. Let's get started. So our goal today is to take two inputs. One is the initial location of an object, and the other is the IMU data from that object, design some motion tracking algorithm, and output the 3D trajectory of that object. The object can be anything. For ease of explanation, we're going to take it as a plane. You'll realize why taking a plane as an example is a good intuitive way of thinking about the problem. Okay? So the problem definition hopefully is clear. Okay? So to be more precise, the initial location is a vector, x0, y0, z0. And the IMU data is essentially composed of accelerometer, which is a vector, ax, ay, az, meaning what is your acceleration along the x direction, along the y direction, and along the z direction. That's what accelerometer gives you. Gyroscope gives you angular velocity along each of these directions as well, gx, gy, gz. Angular velocity meaning how much of theta have you rotated in unit time along the x, y, z direction. And magnetometer gives you magnetic field along the x, y, z directions as well. So you get essentially three vectors from your IMU chip, and these are the inputs, and the output you want is x, y, z as a function of time, because you want to track the motion of the object over time. Clear? Okay. Now, many people think of IMU as a motion sensing device where they think, okay, accelerometer is acceleration. If I double integrate acceleration, I get displacement. So all I need to do is take the initial x0, y0, z0, that's the initial location, plus some double integration of accelerometer, which will give me displacement. So initial location plus displacement will give me the output x, y, z, will give me the output x, y, z that I need. This is typically what people think when they think of IMU, but there's a big problem over here. Okay? The big problem is the following. The accelerometer data that you get, the ax, ay, az, the acceleration in the x, y, and z directions, they're actually in the object's local frame of reference. Okay? What does that mean? As an analogy, if you're inside a plane and you are an accelerometer, let's say, you can measure acceleration. You can measure that you're accelerating ax in the frontward direction, you're accelerating ay in the rightward direction, and accelerating az in maybe the upward direction when you're taking off. Right? So as an algorithm, if you give this ax, ay, az to the algorithm and say, okay, tell me what my motion pattern is, the algorithm is going to say, no, I cannot solve that problem because I do not know what frontward means in the global coordinate frame. Make sense? At the end of the day, I want to say that you're flying from Chicago to New York in some global coordinate frame, on the Earth's coordinate frame. If you tell me frontward, backward, sideways, that's in your local coordinate frame. That doesn't solve the problem. Okay? So this makes orientation important, meaning what is the orientation of the flight with respect to the world, or with respect to a global coordinate frame. Okay? Let's see what that means specifically. So 3D orientation is essentially the 3D rotation needed to transform your local frame of reference into the global frame of reference. If you can understand that rotation, you know what your 3D orientation is. Okay? So look at this analogy. There's a flight which is going in some direction, and it's measuring itself in the front, right, up direction. And then you rotate the flight until the flight's front, right, and up direction coincides with, let's say, magnetic north, gravity, and some other global direction. So how much ever rotation you need to have this local coordinate frame coincide with the global coordinate frame, that will give you your orientation at any given time. Okay? So mathematically, what rotation do you need on your current state to make yourself aligned with the global reference frame? Okay? So how will orientation solve this problem? Suppose you compute orientation. Well, then I'll get my IMU data in the local coordinate frame. I'll compute orientation. Once I compute orientation, I can take my IMU data, and I know what my IMU data means in the global coordinate frame. And from that, I can now do double integration of acceleration, and that will exactly tell me how I'm moving on the Earth's surface, right? Because everything that I'm measuring is now in the global coordinate frame because I know my orientation. I know how to rotate from my local coordinate frame to the global coordinate frame. Okay? Great. And then once I know global acceleration, I can compute XYZ in the global coordinate frame. Okay? So 3D orientation is the key. And now the question is, how do you compute your 3D orientation? Okay? Great. So there are two main opportunities to compute that. One is gravity, and one is magnetic north. Okay? Let's see what that means. The key idea over here is, to compute 3D orientation, is what rotation is needed such that your measurement of gravity is exactly in the downward direction. Right? You're measuring, if you're in some weird tilted view, you're not going to measure gravity in your local downward direction. Only if you become straight, horizontal, will you measure gravity in the local downward direction. Okay? So you need to understand that rotation. And similarly, what rotation do you need to make your local north exactly your forward direction? Sorry, to make your global north in exactly your local frontward direction. Okay? So let's see what that means. If the flight is taking off like that, it is measuring gravity in its local coordinate frame. You rotate the flight until gravity is exactly in its downward direction. Similarly, of course, by the way, it's important to observe that if you just make sure that gravity is in your downward direction, in your local downward direction, that still doesn't give you full orientation, because your flight can be any direction in the horizontal plane, and your gravity will still be vertically downwards. So it only gives you 2 degrees of freedom in otherwise 3 degrees of freedom that you need for full 3D orientation, right? So gravity gives you 2 degrees of freedom, but you still have 1 more degree remaining, and that you can get from your magnetic north, because now you are in some unknown orientation, but then you rotate to make yourself aligned with magnetic north. And once you have that, you have precisely found out what your orientation is. Okay? Great. Now, once you do that, the question is this enough? Okay? Well, this is only enough if the object is static, but not otherwise. Why? Because if the object is moving, suppose there is an object that's moving, that motion pollutes, or rather reflects in the acceleration data. And acceleration is what you need to estimate gravity, right? If you're static, you can estimate gravity, but if you're moving, the acceleration that you have is an aggregate, is a vectorial sum of gravity and your motion, and therefore you cannot decouple gravity from that, and if you cannot decouple gravity, you don't have the anchor to orient yourself horizontally. Therefore, if you're moving, this technique of 3D orientation estimation does not work. Okay? But there's another way of actually computing orientation, which is the gyroscope, which essentially measures angular velocity. So if you know the initial orientation and you integrate gyroscope once, that also gives you orientation. But gyroscope actually drifts because of some of the MEMS properties. And as a result, gyroscope is only good for short time scales, not for long time scales. So this is what state-of-the-art does. Okay? State-of-the-art looks for opportunities when the object is static. When the object is static, it computes the 3D orientation using gravity and magnetic north as the two anchors. And then when the object is moving, it uses the gyroscope to kind of integrate and compute the relative orientation changes, and it keeps doing this. And thereby, it always knows 3D orientation. Okay? So this is the basic algorithm of the state-of-the-art. You first figure out if it's static. If it's static, you use accelerometer and magnetometer, gravity and magnetic north. If it's not static, you use gyroscope. That together gives you orientation, and then you do double integration of acceleration. The main takeaway is, from today's state-of-the-art, is gravity is the main anchor that you need to do 3D orientation. But what if the object is hardly stopping? The object is in continuous motion. Cars, your hands for a long time, balls in sports, right? Then what do you do? And that's where this paper comes in. And if you've understood this, till this point, I'm happy. But if you're still understanding, please stay with me, okay? So the basic idea we have over here is Muse, which is the paper we have, wants to estimate 3D orientation even for moving objects, okay? And the core idea is the following. You know, the Earth's magnetic field is like this, and that is what is measured. The direction of the Earth's magnetic field and the magnitude is what is measured by your magnetometer in your phone. And that gets reflected as a 3D vector, and the projection of that on the XYZ axis is your MX, MY, MZ. So what we want to do is essentially use the magnetic north as the anchor, because when your object moves, that movement does not pollute the measurement of your magnetic field. Okay? But again, magnetic north doesn't give you full orientation. It only gives you 2 degrees of freedom, because if you move perpendicular to the magnetic north, you still cannot say anything from the magnetic north itself. So we want to rely on the magnetic north to give us 2 degrees of freedom, and then use other mechanisms to resolve the additional degree of freedom. Okay? So here is the idea. I'm going to rotate my magnetic measurements until it aligns with the Earth's magnetic XYZ. And now we want to ask 3 questions over here. What does it say about my orientation? Okay? So at some point, if I compute my orientation, and I say, okay, I infer what my magnetic north vector is, and I also measure whatever is the difference between my inferred vector and my measured vector is essentially how much I am off in my orientation estimate. Okay? So then what I do is I compute how much orientation do I need, how much change in orientation do I need, so that my inferred vector becomes the same as the measured vector. Okay? High-level point is, I'm going to use the gyroscope I'm going to fuse the gyroscope data and the magnetometer data carefully to actually figure out what my orientation is. Okay? So the question is, how do you know your magnetic vector? That is also something that you don't know, right? One possibility is to look up your GPS, and if you know the GPS, you can actually figure out the magnetic vector of that location. So that's one possibility. The other possibility is you do it once, you measure, you somehow figure it out once if the object has stopped, and because the magnetic vector is not going to change at that particular area, you can use that magnetic vector all throughout after that. Okay? I'm going to skip through the evaluation because I want to talk about another small part, but the evaluation essentially says 3D orientation with our paper is better than several of the state-of-the-art that exists today. Okay? But here's the second part of the paper, which I'm going to briefly describe to you. Okay, we have 3D orientation now. How do you now estimate location? Okay? Remember we said we are going to turn the plane in the global coordinate frame, which means my accelerometer data also now becomes in the global coordinate frame, and then I'm going to double integrate acceleration. Well, the bad news is, if the accelerometer has any amount of noise, that double integration will blow up that noise, and it is impossible to compute location. Why? Because there is no way for you to figure out whether what you're computing is that good enough or not, because you have no notion of ground truth. Because that noise, there's no notion of compensating for the noise that's getting double integrated. Okay? But here is the good news. If you have any motion model, that motion model should be able to help you bound the errors. So for instance, if I want to track the location of my elbow, I know my elbow is on a sphere where the center of the sphere is my shoulder, right? Whatever I do, my elbow should be on that surface of that sphere. So if I know that information, and now I double integrate, and the double integration says, oh, the elbow location is here, I say, oh, that cannot be true, right? Because I know it's on a sphere of radius r, or not, with the center as my shoulder. So motion models help you bound the error. That's the opportunity that you have for localization. So what we do in this case is one application where we want to understand arm motion. So we take anatomical models of your arm motion and use that as priors into your acceleration double integration unit, and from that we compute. But more importantly, once you do that, you can actually jointly estimate orientation and location. I don't want to get into the details, but what we are saying is, if my motion model tells me something, from then I can ask the question, how much orientation and location do I need to change so that my estimates fit my motion model and my location estimates very well? Okay? In other words, I feed back my location estimates back to my orientation, and I do a joint estimation. Okay? The results are not important in this paper, but still I wanted to show that the median accuracy turns out to be 13 centimeters for arm motion, where we wear a watch, a smartwatch on our wrist, we move our hand, and we get around 12 to 13 centimeters of accuracy. But most importantly, the error doesn't diverge with time, which is one of the fundamental problems with inertial motion sensing. Okay? So in conclusion, conventional systems use gravity as the anchor for 3D orientation. We actually use magnetometer as the main anchor, and then we do a joint estimation using a particle filter framework to basically combine magnetometer, gravity, gyroscope together, along with motion models as priors, to finally solve the localization problem. Again, this is application specific. It works well because human arms have nice constraints. For an arbitrary motion, it might actually be much more difficult. That's all I'd say. Thank you very much.
Here comes to our last speaker of this session. His name is, speaker's name is Lincoln Li. He's a third-year master student at Tsinghua University. And his current interest is visible light communication and also related applications. So if any faculty would like to take like a new PhD student, you can talk to him.
Thanks for the introduction. My name is Li Lincoln. I come from Tsinghua University. I'm going to introduce our work, Rainbow Light. It is a localization system using ambient light and mobile phones. And this work is collaborated with Xiepeng Jin, who is also here as well, and my advisor, Wang Jiliang. There are some existing researches of the visible light positioning, and they are all in high deploying cost or high using cost. For example, some works need special designed hardware, such as spin light or smart light, and they lead to high deploying cost. And some works need strict using requirement, such as Luxapose. It needs to capture more than 3 lamps simultaneously. It leads to high using cost. And some works are dependent on the environment, like light tail and eye lamp. When we change a bulb, we need to do resample. They also have a high deploying cost. And so we present rainbow light as this picture shown. We make an anchor consist of multiple chips. For each chip, we can observe different color from different direction. So when we observe the anchor from different position, we can obtain different color sequence. Overall, rainbow light can measure relative location for a given anchor easily. First, it is user-friendly. Rainbow light doesn't need a strict using requirement. User can capture anchor with any orientation. Second, it is easy to deploy. Rainbow light doesn't need to design specific circuit and only need to perform initialization once. What's more, the anchor can be stuck everywhere. Third, rainbow light is cheap. Anchor is made by polarizer and transparent adhesive tape. And the receiver is most common used mobile phone. And rainbow light can work with light off in the daytime. Now I'd like to introduce the localization basics of the rainbow light. Rainbow light is based on birefringence. When a bunch of incident light pass through a birefringence material, it generates two bunches of refractive light, so-called ordinary ray and extraordinary ray. As the picture shown, we can observe two pencils after birefringence material. Suppose we have a polarizer P1 and a birefringence material S. When the incident light passing through birefringence material is a polarized light, the two bunches of refractive light are also polarized light. However, those two bunches of light have different polarized direction. Suppose we have two bunches of incident light. We can get one bunch of light pass out from S mixed by an ordinary ray from one pair and extraordinary ray from another one. We want to explore which color is shown of the light. Before we move on, I'd like to recall a basic principle, interference. When two bunches of light meet coherence condition, constant phase difference, same frequency, and same polarized direction, it will cause interference. If those two bunches of light contain single frequency, it will show a dark and light stripe. And if those two bunches of light contain multiple frequencies, it will show a color stripe. Now let's come back to the mixed light before. Because the path difference of those two components is constant, they have a constant phase difference. Since they are emitted from same source, they have the same frequency. But they are different in polarized direction, so they don't meet the coherence condition. However, when they pass through another polarizer P2, since only components have the same polarized direction as P2 can pass through, after P2, the two components have the same polarized direction. Therefore, they meet coherent condition. If we use light with multiple frequencies as the incident, we can observe color different with the incident. Now we move the camera and observe the same point as before on the birefringent material. We can notice that the incident angle is changed. Therefore, the phase difference changes and result in color changes. So we can build a relationship between position and color. In system design, rainbow light contains two main steps. One is mapping initialization, and another is 3D localization. From localization basics I have mentioned, we know that we can observe different color from different position. So a naive method is that we can perform sampling in whole 3D space. And during localization, we map color to position directly. But it causes too much efforts. Fortunately, since light beam is transmitted along a straight line, we can map color to observation direction. Therefore, we only need to sample on a certain plane instead of the entire 3D space. We move the MobiCom on the plane and the captured photo contains anchor. Then we extract color of chips on the anchor to derive a map from color to direction. This will reduce initialization overhead significantly. After we get map from color to direction, we can perform localization easily. We capture the photo contains the anchor, extract the chip's anchor, and get corresponding direction from camera to each chip. If we have absolute coordinate of each chip, we can get camera's position easily. In implementation, we use polarizer and transparent adhesive tape to make chips and compose a sort of chip to an anchor. We also write an application based on Android platform. It can extract color on chips and perform localization automatically. We use 2 polarizers and 1 piece of transparent adhesive tape to make a chip and put a sort of chips on 1 anchor. In this scenario, both camera and human eyes can observe the colors. But from our experience, since the chip is small enough, it couldn't annoy people, in fact. But what if people doesn't want to observe the color on the chips? To eliminate color observed by human eyes, we can use 1 piece of polarizer and 1 piece of transparent adhesive tape to make a chip, and put a polarizer before MobiCom's camera. In this scenario, only MobiCom can capture the color while human eyes cannot. However, the color can be changed when we rotate the MobiCom, so we need to address this issue. From our experiment, we rotate camera attached with polarizer P2 and remain P1 fixed. We can notice that there are only 2 stairs of hue values, and they are complementary with each other. Therefore, those 2 colors can be easily distinguished in our system, and thus rotating MobiCom has no impact to rainbow light. In evaluation, we make anchor with 6 chips on it. The diameter of anchor is 20 centimeters, which is smaller than the most of lamp covers. We do experiment in our meeting room at the right side. We put a transparent board with coordinates and do experiment by taking picture on coordinates and then calculate the localization error. First of all, we move the board from 0.6 meters to 3 meters. We can find that the localization error is applicable in daily use. The localization error on 2D plane is around 5 centimeters. When we move camera far from anchor, error in distance between anchor to camera is gradually bigger. This is because with the distance from anchor to the camera comes longer, we move camera along that direction can lead to smaller incident angle changes. Therefore, change of color is not obviously. To measure the influence by light source, we use multiple bulbs in 4 dimensions to do our experiment. We use Philips 6.5 watt LED bulb with color temperature 6000 Kelvin to perform mapping initialization, and test the localization error with different powers, color temperature of bulbs, manufacturers, and types. With different power and manufacturers, the localization doesn't have much difference. However, when we change the bulb with color temperatures to 3000 Kelvin, the localization becomes bigger. What's more, if we use different type of bulb, such as fluorescent or incandescent bulb, it also leads to a larger localization error. This is mainly because the spectrum emitted from different power and different manufacturers doesn't have much difference, but changes more with different color temperatures and types. However, even if the error becomes big, they are also applicable in daily use. We also evaluate rainbow light when we put polarizer P2 in front of the camera. We change the orientation of mobile phone and calculate localization error. With pitch and yaw, since color doesn't change more, so the influence precision is slightly. With rotation, since the color changes with polarizer P2's rolling, it causes a huge error on z-axis, but the error on the x and y-axis are remaining small. Because rainbow light only depends on the incident spectrum, it can work even with light off in the daytime. And our experiment shows it can work well. It extends application scenarios significantly. In the future, people can use rainbow light to locate themselves and launch indoor navigation. And it can also be used on robots in intelligence warehouse. With blooming of self-service supermarket, rainbow light can help to locate commodities. And so for a conclusion, we present rainbow light, a high-precision 3D ambient light-based localization system. It is user-friendly, easy to deploy, cheap, and can work with light off in the daytime. Thank you for your attention.